In the last video, you learned how to use the equations on your reference page to help calculate the wavelength, frequency, or energy of electromagnetic radiation. In this video, you will discover that the electrons in atoms emit or absorb electromagnetic radiation in order to move around inside the electron cloud, but they only absorb or emit specific wavelengths, which correspond to specific amounts of energy called quanta. In addition, each type of element absorbs and emits a unique set of wavelengths. This property was used to discover some elements and was used to help determine the location of electrons in the electron cloud. The location of an electron in an atom is described by a set of 4 quantum numbers. Before we can discuss how the atomic spectra were used, you must first understand what a spectrum is. Pictured on the screen are 3 different types of spectra. The continuous spectrum shows all possible wavelengths. When we see a rainbow, we are seeing a continuous spectrum in the visible range. The emission spectrum has a black background with only certain wavelengths shown. These particular wavelengths are the only ones that are emitted by the electrons in the atom or atoms present in the substance. Each wavelength corresponds to a specific amount of energy that can be calculated using the equation energy equals Planck's constant times the speed of light divided by the wavelength. The absorption spectrum looks like a rainbow with certain wavelengths removed. These particular wavelengths are the only ones absorbed by the electrons in the atom or atoms present in the substance. Notice that the emission spectrum lines match up perfectly with the absorption spectrum lines. This is because, for a given element, the energy emitted is exactly the same as the energy absorbed. Every element produces a unique emission or absorption spectrum, which is sometimes referred to as its atomic fingerprint. This is how several elements, such as helium, rubidium, and cesium, were discovered. When elements emit wavelengths in the visible range, we can see the colors. Elements or different mixtures of elements are used in neon lights and fireworks to produce the different colors we see. Neon lights that actually contain neon give off a reddish-orange light. Sodium vapor lamps, used in street and highway lights, give off a yellow light. Barium is used to give fireworks a green color. Emission spectroscopy is a useful technique. Forensic scientists can use this technique to determine the identity of a poison in a sample. Environmental scientists can identify pesticides in the environment. It is also used by astronomers to determine the composition of stars light years away. Niels Bohr studied the emission spectrum of hydrogen to determine that electrons are on different energy levels. From this, he came up with a planetary model of the atom, which was discussed in the last unit. So why do electrons in the atom absorb and emit light? They absorb and emit light to move to different energy levels in the electron cloud. All of the electrons in this sodium atom are in the ground state. That is, all the electrons are in the lowest possible energy levels available. The valence electron, or outer electron, in this sodium atom will absorb a particular wavelength of light in order to move from the 3rd energy level to the 4th energy level. This atom is now in the excited state because an electron has temporarily moved to a higher energy level. To move back down to the 3rd energy level, the valence electron will have to emit or release energy. It will release exactly the same wavelength that it absorbed, assuming it moves back to exactly the same position from which it started. This specific amount of energy that an electron absorbs or emits is called a quantum. The location of an electron is described by a series of 4 quantum numbers: N, L, M sub L, and M sub S. You can think of these as being the address for an electron's probable location. Electrons contain fixed amounts of energy. The amount of energy they contain determines where in the electron cloud they are located. The more energy an electron has, the farther away from the nucleus it can be. Electron clouds are made up of energy levels, represented by the quantum number n, which are like rungs of a ladder, but they are not equally spaced. A Bohr model, like the one pictured, is a decent two-dimensional representation of this concept, but you must remember that electrons do not orbit the nucleus like planets around the sun. Notice the values of n located on the rings, or energy levels, of the Bohr model. The higher the value of n, the farther away from the nucleus the electron is, the higher the energy level it is on, and the more energy the electron must have to stay there. The maximum number of electrons in any energy level can be found using the following formula. The number of electrons equals 2n squared. You will need to memorize this formula. On the first energy level, the energy level closest to the nucleus, n equals 1. So the maximum number of electrons that could go on energy level 1 is 2 times 1 squared, which equals 2. On the second energy level, n equals 2. So the maximum number of electrons that could go on energy level 2 is 2 times 2 squared, which equals 8. Pause the video and calculate the maximum number of electrons for the rest of the energy levels in the chart. When you are ready, continue the video for the answers. The sublevels, represented by the quantum letter L, are designated by specific letters. The sublevels you need to know are S, P, D, and F. Electrons need different amounts of energy to be on the different types of sublevels. S sublevels require the least amount of energy, while the P sublevel requires more, then the D, and then the F. The number of sublevels on an energy level is equal to the energy level number, or N, for that energy level. So energy level 1, where N equals 1, has only one sublevel, which is the S sublevel. Energy level 2, where N equals 2, has two sublevels, an S and a P. The S sublevel for energy level 2 is larger than the S sublevel for energy level 1, so the electrons are able to move farther away from the nucleus. Energy level 3, where N equals 3, has three sublevels, S, P, and D. These sublevels are even larger than the sublevels on energy level 2. Energy level 4, where N equals 4, has four sublevels, S, P, D, and F. These sublevels are even larger than the sublevels on energy level 3. Orbitals are represented by the quantum number m sub L. Each sublevel contains a certain number of orbitals, and each orbital has a different shape as specified by a certain mathematical equation called the Schrödinger equation. The s sublevel has only one orbital, and it is a sphere. The p sublevel has three orbitals. The shape of each orbital is sometimes referred to as a dumbbell, and each orbital lies along either the x, y, or z axis in a three-dimensional space. The d sublevel has 5 orbitals. 4 of the orbitals look kind of like two p orbitals stuck together as a clover leaf. The 5th orbital looks like a p orbital inserted through a donut. The f sublevel has 7 orbitals, and I'm not going to try to describe the shapes of these, but here's a picture of them for your viewing pleasure. Each orbital can hold a maximum of 2 electrons. It can hold less than 2, but never more than 2. The maximum number of electrons on a sublevel is the number of orbitals times 2. The s sublevel, which has 1 orbital, so 1 orbital times 2 electrons gives a maximum of 2 electrons. It can have less than 2 electrons, but never more than 2 electrons. The p sublevel